All right, let's start. Hello, everyone. This is Dr. Yuzo. Today is Monday, our fourth lecture. And first of all, can you guys hear me well? And also being able to see my share screen? Good. Thank you. Thank you. Yep, good. Let's continue. So here by this Gantt chart, I hope everyone can be aware that we are at this cell, this particular one, which is the very last lecture of module 2. And from Wednesday on, we're going to start the third module, block diagram. And also by the end of the third module, we have midterm 1, which means next Monday here, we will have a review. Okay, we will have a review for midterm 1. Okay, it's the first thing. Second thing is, according to the survey results, which is due today, it seems everybody is fine with the time here. So be it. Okay, we will have midterm 1 at this time. Okay, this is the time exam. And then let's come to the doc camp to talk about our module 2. So here, once again, we begin with reviewing the module 2, what we have done. Okay, so first one here, this module is basically presenting knowledge like this. Okay, this is the overall picture of the module. So the physical system or component, either mechanical or electrical, could be modeled or described by a differential equation in time domain based on physics. Physics, the basic principles. And then the differential equation can go back and forth to the frequency domain transfer function, so-called, by conducting the Laplace transform or the other way around, inverse. Okay, so we have done pretty much the one-way Laplace transform and the other way, the inverse Laplace transform. Okay, so we have done both way, here and here. Okay, we had some examples showing the details. Okay, so today, very last part of the module 2, we're gonna really talk about, or say summarize, the basic, very basic, the physical, or say electrical and mechanical system component, okay, and the frequency domain representation of them, or say the frequency domain, nothing but transfer function. Okay, kind of develop some tables to summarize everything together, okay, and make them organized. Okay, and then mechanical system, we're going to talk about two types of mechanical system. One is translational, and another is rotational. Okay, and we have two versions of Newton's law and relationship among those variables. Okay, this is a little bit of review at the beginning. So let's start. Okay, let's start. Number 4, very last part. Okay. So let's begin with the electrical. Let's begin with the electrical, which we are more familiar with, electrical network or system transfer function. Specifically, what are we gonna study? Very simple. Okay. Yeah. Voltage, current, and what? Third one is home. Anyone knows?
Power?
No, power is a quite fair guessing. That's a good answer, actually. But here is actually talking about the Ohm's law. So the third one is what? Thinking of Ohm's law is what?
Distance.
Impedance. Impedance. Okay, impedance. Impedance, what is the symbol for impedance? Z, right? Z. So it's impedance. Okay. By the way, what's the relationship between the impedance and the resistance? Anyone? What is the relationship?
Well, both of them are in units of ohms.
Say that again.
Both of them are in units of ohms.
Very good. That's a common point. And I received another answer from Noah. Resistance is real part of the impedance. Excellent. That's the best answer. Okay, excellent. Excellent answer. Impedance, resistance plus J what? Anyone? J what? X, which is reactance. Excellent, Jeff. Good. Jeff and Noah got the correct answer here. So impedance is kind of a total impedance, including the resistance and the reactance. Who are introducing, or say, who are contributing the reactance then? Because we know this guy is from resistor, of course. And who are contributing the reactance? The rest of two, right? Only rest two. Inductor and capacitor, right? Good, very good, very good, very good. Yeah, good. So we just talk about the basically IV relation, or say the Ohm's law. Okay, let's summarize the thing together. It's very simple, but we want to make them organized. Okay, so we just talk very basic things. Okay, resistor, inductor, and capacitor. Right? Three components, very basic. Three components. The second column here, we're going to talk about time domain modeling, time domain model, or say time domain expression, and corresponding ice domain, or say the frequency domain model. Okay. So in time domain, what do we have for resistor? Very simple, right? Very simple. The resistance just equals to the voltage in terms of time divided by current in terms of time. This is nothing but Ohm's law we learned from 235, right? And then we also know that to obtain the frequency domain corresponding transfer function, what we need is Laplace transform. Okay, well, we need just Laplace transform. This is the linkage between the time domain and S domain. Right? So if you apply a Laplace transform on this time domain differential equation, well, of course, we are not seeing any deep derivative or integral, but essentially this is also considered as a special case in differential equation, right? So applying Laplace transform on it, what we got? What we got is this. Right, what we got is this. Resistance itself, which is constant, just equals to capital V of S divided by, capital I of S, right? That's very, very simple. Yeah, very simple. And again, this is nothing but impedance of the resistor. Impedance of the resistor is nothing but the resistance itself. Similarly, we have inductor. Inductor, what is the time domain model? IV relation, what is it? Anyone recall? For inductor, anything?
L di dt.
L di dt. L di dt. L di dt. L di.
And just out of curiosity, why is it sometimes we hear about negative L di dt?
Negative L di dt. You're saying?
I don't know if sometimes in like motors they refer to negative L di dt. Is there any reason why the negative's there? Or no, is that just...
You mean there's a negative in front of L?
Yeah, is it just like the polarity is they're going the opposite direction with it? Like
No, you gotta understand. First of all, this is what? V of T, right? That's the voltage of the inductor.
Okay.
The voltage of inductor might reverse direction. However, the current won't.
Okay.
Okay. The voltage might reverse. Okay. Positive bouncing between positive and negative, that's possible. Okay. However, your current won't. Because as you know, the current through the inductor cannot change instantaneously, let alone change the polarity easily. No.
Okay.
Yep. So the voltage, yeah, might change polarity. That's possible. However, the current won't. Okay, not instantaneously. That takes a lot to change the polarity, or say the direction. Okay, takes a lot to change the direction. Okay? And to this guy, if you apply the Laplace transform, what is the result? At left hand side, going to be V of S. That's very easy. V of t becomes capital V of S. That's easy. How about this one? L di dt becomes what?
Well, di dt should be f of s. It should be, for the inductor Laplace, it should be L s I L of s minus L I c of naught. Or sorry, I L of naught. So
Good. Basically, John is right. Okay, so basically, John is right. So first of all, L remains as L. Derivative, Laplace on the derivative, gonna give you a S. Okay, recalling the previous example we did in last lecture, right? And capital I of S. And we once again assuming what? Zero initial values. Okay, we are assuming zero initial values. Makes things easier. Okay? This is how we end up with this. And or say the reason is follow the handout, one of the handout formula over there. Okay, Laplace transform of a derivative is going to give you a S. Okay, that's why. All right, to capacitor, what do we have? This guy, right? This time is not the voltage, but the current of the capacitor is equal to capacitance times the derivative of the voltage across it. Okay. So your current might look like any shape. However, your voltage cannot change easily. Okay, the voltage cannot change easily, right? So apply the Laplace transform on it. We end up with this, right? End up with this. Okay. This is the capacitor and the inductor. Of course, we can derive the impedance. What do we see? This is what? Impedance. Impedance 2. So in black color, I'm deriving the impedance of inductor and the capacitor in frequency domain. Okay. So in frequency domain, the inductor is what? Nothing but inductance times S. Capacitor is what? Is 1 over capacitance times S. Right. But that's the thing we are really care about. Okay. The impedance in frequency domain. Okay, in frequency domain. And we will go through examples to see how we're going to use them. Okay, this is the electrical. A little bit more here. So from here, the reciprocal of the impedance equals what? What is it? What is this?
Admittance.
Admittance. What I'm saying is that to admittance, you have another version of Ohm's law, right? Admittance. What? Admittance basically times voltage equals to current. Does it make sense? This is Ohm's law. Okay, that's the Ohm's law. Okay. Because to impedance, you have what? Impedance times current equals to voltage. However, to admittance, is admittance times voltage equals to current. Okay. This is the electrical. So move on to mechanical.
Do you remember the letter for admittance?
Yeah, anyone can help us recall? What is the admittance? What is the letter?
Isn't it Y?
Very good. Very good. Noah is right. Is what?
What?
Capital what? Very good. Very good. Is what? Very good.
Why do they denote it with G sometimes? Or is that
Why what?
just, like sometimes they'll say admittance is equal to G?
Yeah, G. Can anyone link the admittance to G then? Anyone knows? What is G? Actually, is there anyone knows who is G?
Does it have to do with the unit of like admittance?
Not quite. The unit admittance is what?
Siemens, right?
Siemens, correct. Siemens, correct. The G's unit is what? The G's unit is Siemens as well. All right. Just like a impedance here. Just like impedance ohm 2. Doesn't make sense, right? So all of them are uniform. Okay, is ohm. Okay. And going back to G, here Noah and Yadav said G is acceptance. I think is close. Is it called acceptance or conductance? Which one? My memory is a little bit blurred too, actually.
G. It's conductance.
It's conductance, right? Yeah, I think I remember it's conductance. Okay. And we have resistance, reactance, conductance, and what? We have 4. Okay. Unfortunately, we have 4. Or if you including the impedance and admittance, we have 6 actually. Okay. Once again, impedance equals to resistance plus J times reactance. Admittance equals to what? Conductance plus J what? Anyone knows? The 6th one. Number 6, the last one. Susceptance. Correct. Okay, Jeff is right. Very good. Very good. Jeff has done 341, right? I think that's the reason. Yep. Good job, Jeff. Very good job. Very good job. Okay, so susceptance is B. Okay, is B. Okay, G plus JB equals to Y. Okay, this is the admittance equation. All right, we have to move on here, and more details about them. Well, it's actually 341 power systems knowledge. Anyways, now let's talk about mechanical. Yeah, let's talk about mechanical here. Okay. Mechanical. Network power system transfer function. First of all, just like what we did here in red, what signals or say what variables we are discussing in mechanical? What are they?
Mass, usually spring force, right?
But mass is actually considered as a constant rather than variable. So the really things we really care is force introducing what displacement and the further the velocity, right? Of course, this is for the translational system. To the rotational system are different. Okay, they're different, right? To rotational system is not horizontal displacement, but angular displacement and angular velocity. It's not forced either. It's not forced. So instead, what is it?
Torque.
Torque. Very good. That's torque. Very good. Okay, 2 is right. It's nothing but torque. Okay, so force to versus torque and displacement versus angular displacement, and so on. Okay, so let's talk about first of all the translational. Okay, translational system. Okay, in where we can study the relationship among force, displacement, and velocity. Okay, yes, and we're gonna have another table obviously. The first, the basic component is spring. Second is whiskers. Last one is mass. Okay. Still, 2 column here, time domain and the frequency domain. So first of all, these time domain to spring is actually the force is equals to a constant k times x of t. X is what? What is x? Displacement. Okay, x is displacement. Okay, x is displacement. And the corresponding Laplace transform result is gonna be capital F of s equals to constant k remains times capital X of s. Okay, so you can rate here as the force equals to the product between spring constant times the displacement introduced. Right, it's very easy behavior. Next, whiskers. The force applied on the whiskers damping. We say whiskers damping. What had happened? First of all, is introducing the what is it? Velocity. Yeah, velocity. And further, you link the velocity with the displacement. Velocity equals to what? In terms of displacement. This is very basic physics, right? Velocity and the displacement. What's the relationship? Derivative. Here we go. Good. Okay. Lucas is right. Derivative of the displacement is equals to velocity. And now we apply the Laplace transform on it. And we're going to end up with this, right? Force equals to F sub V. The F sub V is, of course, whiskers constant. Times V of S, and also equals to S times X of S. Because once again, we are seeing a derivative here. The Laplace transform of the derivative going to give you a S here. The last one is mass. The mass is equals to what? This is Newton's law, Newton's second law, right? force equals to mass times the derivative of the velocity, right? Or say mass times what? Acceleration, right? And further equals to mass times second order derivative of velocity with respect to the time, right? So Newton's second law. This is nothing but Newton's second law. And the Laplace transform result is equals to m times s v of s, and also equals to m times s squared x of s, right? So in the translational system, if you're seeing spring, you're seeing viscous damping or math, and then giving certain force, what is the result? It's displacement or velocity. You can find based on these basic principles. All right. All right. This is the translational. Let's talk about the rotational. Same thing we're gonna do. Rotational system. Once again, recalling what we're gonna study. These three things: torque, angular displacement, and angular velocity. Right. So this time, once again, time domain and frequency domain. And we're going to talk about spring, viscous damping. These two things remain in the rotational system. The third thing, mass, well, not quite significant. Instead, what we have?
Inertia.
Inertial. Very good. Very good. Yeah, very good. Very good. So here is right. It's inertial. It's inertial. We need to study these three. Yeah, we need to study these three. Let's see. Time domain, what do we have here? The torque, lowercase torque, is tau. Is constant k times angular displacement theta of t. Angular displacement. Okay, this is torque. And this is the spring rotational constant. Okay. And here, the torque of T equals to D times angular speed, omega T, and then D times derivative theta dt. So this guy is angular velocity. Right. Omega is angular velocity. You know this very well, actually. Which is further equals to the derivative of the angular displacement. That makes perfect sense. The last one is the inertial. Anyone know what is the inertial kick in to the torque relation? What is it? Torque equals to what in terms of inertial?
Should be J. They usually call it J D
Very
squared
good.
theta T over dt squared.
Yep, John is right. So first of all, link to the speed in this way. Further link to the displacement in this way. Right? So J is the inertial. Back to here, D is the viscous, or say damping constant. Right. Yeah, inertial is represented by capital letter J. Okay. We'll give you guys kind of 2 minutes to populate the other side. To populate the last column. 2 minutes. Go ahead. All right, basically, this is as easy as capital T, okay? Torque S domain, capital T of S equals to constant remain. It's a tricky part. The capital letter of the theta have the similar look, however, just what? Bigger, right? Bigger. Becomes bigger. There's some muscles during the summer vacation, maybe. Here, the second to the damping, T of S equals to D constant remains, and omega. What is the capital letter of omega? Well, we are talking about capital letters, the Greek letters. Omega is what? It's like this, right? Omega. It's a symbol of the, you guys know the Omega watch, very expensive luxury watch, right? Omega. And D times S, theta, bigger theta, stronger theta, or say. The last one, T of S equals to JS omega of S, also J times S squared, stronger theta of S, right? These are 3 tables basically summarizing all of the basic physical system components behavior, based on which we can further to derive the system transfer functions. Okay? Because these are components, we can derive a further more complicated system transfer function based on these. Right? Any questions so far? All right, if everything's fine, then let's go through some examples here. Let's go through some examples to see how we really use them. Okay? How we really use them. Let's begin with the electrical example, which should be easier. Okay. So number 5 examples. Example 1. Let's talk about let's find transfer function from circuit below. Of course, never forget, okay, never forget to be noticed, okay, who is input and who is output. Okay. Without these two information, without these information, you can't do anything regard transfer function. It doesn't make any sense. You don't know even who is the input, who is output. That makes no sense to try to derive the transfer function. Okay. So who is the input in this particular example? V of t. Output I of t. Of course, they're going to be labeled in the circuit. Okay. The circuit is like this. Okay. V of t, input source voltage. Yeah, one resistor, one inductor here, another resistor here, and the one capacitor here. Resistance, inductance, and capacitance labeled as R1, R2, L, and C. Okay. Yeah, everything is in terms of symbols rather than specified values. All right, what do we do to such kind of a problem to find a transfer function between these two variables? Okay. Step 1 you should do is Laplace transfer. Laplace transfer. What does it mean is this. The given circuit remains same, however, instead of time domain, inductance, capacitance, of voltage, and resistance, we are converting all of them into S domain model because we just learned these. Remember, we just learned this. We convert everything RLC to what? Impedance. Impedance of R1 is what? R1 itself. Impedance of R2 itself. Because going back to here, this table, the impedance of the resistor, just the resistance itself in frequency domain, right? L, what is impedance of L? Here. LS, impedance of C is what? 1 over CS. So we got everything. Yeah, we got everything. We got everything here. Does it make sense? So Laplace transform, done. Okay, much easier than we thought. Pretty much here we are doing RLC all into S domain impedance. All right, and then we move on to step 2. Step 2 is the time for us to start write equations. Well, given system or say network is a circuit with one source and voltage source and bunch of impedance. What do we do? How we come up with equations? It's very simple. It's very simple. Never forget what we learned from EC 235. Okay, that's the basic of everything in this major. KCL or KVL. Okay, KCL or KVL. Okay. It's as universally valid method. Okay, it's not only working for certain electrical system and do not for the rest. No way. Okay, it's universally valid method. So what matter is we are seeing a circuit like this. It's just a matter of node or mesh, right? Which one we want, right? So here, let's just try mesh, yeah, followed by nodal, conducting mesh to this circuit. What mesh equation? Well, first of all, we are seeing two meshes. Okay, the two meshes, two equations. Two meshes, two equations. All right. First mesh is inside of here, right? Inside of this mesh. I'm defining the rotation direction as clockwise. Same thing for mesh 2. Same thing for mesh 2. So to write mesh, guess what? We need to assume two mesh currents, I1 and I2, respectively. Does it make sense? Therefore, to mesh 1 here, we are rotating, right? Rotating and then seeing negative V of S because we can't come across the negative polarity here first, followed by positive. So negative VS plus R1 times what? I1 of S, right? And then what? The voltage across the LS here. Following this polarity, then what do we have? Impedance times the current equals to voltage across it. And what is the current? Bless you. That's all right. So impedance times the current. So what is the current through LS then? What's the current? I1 minus I2, right? Does it make sense? So this is pretty much one loop, and sum of the voltage, all of them equals to 0, right? So LS times I1 minus I2, we get that. This is mesh 1. So mesh 2, similarly, we have 3 voltage involved, right? So LS times I2 minus I1 this time is the voltage with this polarity inside of this mesh and following the clockwise rotation direction, right? Times R2 times I2 of S plus 1 over CS times I2 of S as well, and total is 0 again, right? See any questions regarding meshes? You might have a little bit different way to write the equation. However, it should end up with the same equation. Okay. Should end up with the same equation.
Is the I of t, that's assuming it's out of the
very good, very good. I was about to give that. I of t, where is it? It's actually here.
Okay.
In the exam, it's definitely going to be given. Okay, as I said at the beginning, if these two are not clear, then it's meaningless to go any further. So, yes, input output definitely labeled clearly in the circuit or system, and therefore, to here, after the Laplace transform, it becomes capital IFS, and you obviously keep in mind I2 is what? Who is I2? Nothing but our IFS. Correct. Okay, correct. Okay, this must be clear. Kevin is right. I2 is nothing but IFS. Okay, this must be clear. Okay, IFS is nothing but I2. So we are seeing, well, if we count this black third equation as one of the equations, then we have how many unknowns? How many equations? Well, 3 equations, of course. How many unknowns? How many? It's 3 equations. How many unknowns? Anyone?
2 unknowns.
I'm sorry, what?
There's 2 unknowns, right?
2 unknowns. What?
Well, because I1 and I2 are the unknowns in this equation.
Yes, I1, I2.
Yeah, we're given what the source voltage is, I'm assuming, because that's an input, right?
Well, that's the mistake the students always have in mind. Listen very carefully, everybody. Listen very, very carefully. Let me give a note here. Okay. Note very, very carefully. Input V of t is what? Not given. And then will never be. Right. What's the sense behind this? What's the sense? We are studying the system behavior, not caring, or say not taking into consideration who is the input. Does it make some sense? Say you design a system, and this system works in certain way that you're trying to model in this frequency domain as a transfer function, right? We do not care, or say the system should not care who is the input. In other words, no matter what is the input, your system should behave in the same way in terms of the transfer function. Does it make some sense? Okay, try to establish this kind of idea, okay? Because when we design a system, we always kind of think in this way. We don't care who is the input. We only care about the system performance, system behavior. No matter what is the input, my system behave the same, which is the transfer function, which is according to the transfer function. Does it make some sense?
So basically, we're given an output that it wants, and we're trying to find what the input that works for it.
No, actually, not quite. How the input works here is like this. We are studying the system behavior, right? We only care about system. We don't care about who is the input because they're supposed to be the same, the behavior. However, if we want to know what is the output, specifically what is the output, who is the output, then we must know a particular input, because one particular input is introducing one particular output. So if we are studying the system itself, it doesn't matter who is the input. Therefore, we are not able to who is the output either.
Okay.
Yep, this is the idea. This is the idea. Okay. The input won't kick in until we would like to find out the particular output. Okay.
So it's just the generic equation for the components we have. So then if we decide to apply 5 volts, we can plug it in, find the answer, or if we apply 500 volts, we can find the current because we have the generic equation.
Yes, basically that way. Okay, because like outputs, because the transfer function equals to output over input, right? In other words, what? The output equals to the input times the transfer function. Does it make sense? Therefore, when we study the system, this guy is the system, okay? This guy is the system. Who is designing it? Who is designing the system? We, as the engineers. Input is up to whom? Input is up to the customer, okay? Out of our control. Does it make sense? Customer is asking you, and of course, paying you to build a system to fulfill some requirements of the performance. And then given the system, the customer gonna give any input they want. Okay. So your output is determined particularly by a particular input. Therefore, input and output, what? Up to customers. We are responsible of the system design. Or in other words, the customer cannot complain, well, your output is a crap, or say too bad output. And then I mean, they cannot complain us for any particular bad output, right? Because they need to tell us what kind of input your input, right? Say you're trying to mess up the system, you give a messed up input, then of course output can be messed up too. Does it make sense? However, the customer gonna be absolutely fair to complain to you that you're giving me a bad system because I'm giving a decent or reasonable input. However, the output correspondingly doesn't make any sense. That's the system's more functioning. It's our responsibility. Does it make sense? So try to establish your idea. Okay, differentiate the input output, these two specific signals with the system performance. Okay, try to differentiate them, separate them to consider. Okay, your output is absolutely up to one particular input. Okay, output, of course, absolutely. However, your system transfer function is something you really care about. Okay, does it make sense now? Such idea not only valid for this course, okay, but also valid for any electrical engineering design. Okay. Any questions? All right, then come back to here. How many unknowns then? 4. Okay, 4 unknowns. Who are they? Input unknown. Okay, input unknown. Output unknown. I1, I2 unknown. So 3 equations, 4 unknowns. Okay. 3 equations, 4 unknowns. What's the conclusion? Cannot find any individual unknown. Does it make sense? Because you have one less equation. Of course, you can't find any individual. Okay, individual, no way. Okay, you find who is V, who is I, who is I2, who is I1. No, you can't, because Only 3 equations. And trust me, you're not able to come up with any of extra distinct. Okay, you can't. You really can't. Okay. We have done. It is what it is. It's just one less equation. Therefore, we can't find any individual unknown. However, it's normal, and it doesn't matter. Why? We can find the transfer function, okay, which is output over input is a ratio between 2 unknowns. Okay. So mathematically, we can't find any individual one. However, absolutely can find a ratio between any 2 of them. Does it make sense? I'm saying, any questions? This idea? So it doesn't bother us to find the transfer function. Okay, we are absolutely fine, and because transfer function is a ratio between 2 unknowns, we absolutely can do that. Okay, we can't find I numerator individually. We can't find the denominator v individually either. However, we are able to find the ratio between them, right? And of course, here, how to find it? Let me provide some detailed algebra here. Provide some detailed algebra here. Look at these 2 equations. Look at these 2 equations. Okay, how to find them? You want to organize them into such format that combining all of the factor of the unknown in this way, right? I think if you definitely have done the differential equation, and in differential equation, I don't know how much linear algebra you guys learned, because based on that knowledge, what you see here is like this, right? This I of s is one unknown. I1 of s is another. You combine all of the factor coefficients of them to write it into this format. Right. Coefficient times I of s plus another coefficient times I1 of s equals to a constant. Right. Second equation, same way. A coefficient times I of s plus another coefficient times I1 of s equals constant at the other hand of the equal. And what's the benefit of writing the 2 equations in such way? This is the matrix, right? This is the matrix. And how to solve this? You guys know you guys know this, right? Have you guys learned Kramer rule from any math class?
Yeah, don't you get one of the variables by themselves?
Say that again?
Like you would subtract the 2 columns and try and get one of the variables by themselves, and the other one to equal 0.
Doesn't sound quite like the Kramer rule I mentioned. But anyways, maybe they're same. Not quite sure, but Kramer rules is like this, right? If you're looking for I of s, which is the first unknown here, it equals to a ratio between 2 matrix determinant. This is Kramer rule. What is the 2 matrix? The denominator matrix is the matrix containing all of the coefficients of two unknowns. Negative ILS R1 plus LS plus R2 plus 1 over CS, and then negative LS. The numerator is a matrix keeping the same second column here, and replace the first column entries with the constant on the other hand side of the equal. And how to find the determinant of 2 by 2 matrix? This guy.
BS
Product.
times negative LS minus
Correct.
minus
Correct.
R1 plus LS times 0.
Exactly right. Yeah, that is correct. Okay. So the main diagonal product minus the off diagonal product, right? The same thing here. So LS squared, right, minus R1 plus LS times LS plus R2 plus 1 over CS. That's it, right? Right. This is I of S. And obviously, we don't need to find I1 of S. Okay, keep in mind, we only need to find what? A relationship between I of S and V of S. You got to keep our target, or say the goal, in mind. Right? We only care about I of S and V of S. We don't need to worry about the I1 of S. Right? But if you're looking for I1 of S, because I want to finish a complete version of Kramer Rule, right? Have you guys learned the Kramer Rule? Denominator matrix remains same. Have you guys learned this before?
Yes.
Good. Which class?
We are still like we have to learn in the class 302 right now.
And before the 302?
Before we learned in high school.
High school?
Yes.
Oh.
Yeah, I don't remember ever seeing it.
Really?
It's been since I've been in high school math.
They show it a lot simpler in high school. It's just numbers.
You mean this one? Well, I mean, if this is not quite clear, I can provide some extra information, but because I can't remember where I learned it. But the thing is, if you guys using TI calculator, probably you guys can even do this in the calculator. Yeah, linear algebra at delta. Yeah, might taught this. Yeah, this is linear algebra, as I said, linear algebra knowledge. Yes, not something very, very difficult. But if you didn't take the linear algebra in the delta, have you guys learned the linear algebra knowledge in Math 262? Have you guys learned anything in Math 262?
I mean, our class talked a lot about the Laplace and stuff like that. I mean, is that what you're referring to, the linear algebra? Equations and solving for equations of Laplace, systems of Laplace equations?
Laplace is not really the linear algebra knowledge. linear algebra is like an equation like these. How to solve it, or say how to build up a matrix to solve it. That is linear algebra.
We saw that on 302 with Clark.
That's good. That's good. That's good. I believe Dr. Clark taught that because Math 262 probably didn't provide sufficient linear algebra. But it's good. Okay, but however, 202 is not the prerequisite of this class. That's why I asked. Okay. Not everyone here is taking 302 at the same time. Okay. All right. Anyways, this is the one example. Now, let's do this. Following the same idea, the same procedure, let's say. Do one exercise for the rest of the time. Okay. Use Nodo to solve the same transfer function. V of s over I. Oh, I'm sorry. This is I of s over v of s. Just come up with the equation. Okay. Come up with the equation. Oh, by the way, yes, probably didn't clarify this very well. After having this equation here, what you're seeing is the one equation, including two unknowns circled in red, I and V, right? Only two unknowns in one equation. What you can do? Just derive I over V equals to what? That's it. One equation. Two unknowns, I of s and V of s. The rest of terms are what? All constant. Right? So what you can do? Derive the ratio between them. Absolutely doable. And that's it. Okay, this is how you find out the transfer function we need at the end. Okay.
So this is why the Bode plot gives us, in terms of gain or dB, we usually convert it to gain as a function of frequency, right?
Don't go that far to the Bode plot. Just this one gonna give you the transfer function. Based on that transfer function, you might go further to find a Bode plot. That's all right. That's fine. However, here is not only giving you gain; it's giving you the whole picture, the transfer function, based on which you can find the frequency domain response, the Bode plot for magnitude and phase angle. Yes, you can. But that's the second step, not the first step.
Okay.
Yep. All right. So now, folks, following the same procedure, use Nodo to solve it. Again, first step remains as Laplace transform. You guys, impedance is for everything. And then come up with nodal equations. Okay, come up with nodal equations. A little bit, pretty much a little bit review of 235. Okay. Okay, go ahead. Give you guys 5 minutes. Go as far as you could. All right, let's see. Basically, the node we want to choose to write KCL is up here, right? I mean, no other reasonable node we can pick in this circuit. So to write KCL, because the nodal means KCL, and then here we involving 3 currents, obviously. So if you're assuming the current's direction like these, and these, we also need to assume the voltage at this node, right? Let's assume this is V1 of S. And then what is the resultant KCL at this nodal? It'd be V of S minus V1 of S, and then divided by R1 equals to V1 of S divided by the impedance of LS plus what? V1 of S, or say V1 of S minus 0 divided by what? The total branch impedance equals to R2 plus 1 over CS. Right? One node, one equation, no problem. No problem. However, we need one more equation, right? Why we need one more equation? Anyone knows?
You want to have V1 in terms of IT.
V1 in terms of IT, correct. Basically, Sawyer is correct. We need another equation to involve I, okay? Because we need to find I over V, right? However, this equation doesn't even have I, so it doesn't work sufficiently. Okay, so we have to have an equation to involve I. What is the equation could be then? It's very easy, actually. Just Ohm's law along this branch. I of S equals what? V1 of S over R2 plus 1 over CS. That's it. Well, of course, and then you need to count, right, to see 2 equations. How many unknowns? How many?
Three.
3. Good. V1 I done. Okay. So here we need to repeat the idea that, well, we are not able to find any individual unknown. However, we can find the ratio between any 2 of them, right? That's the repeating that idea. What we need to do is just go through the algebra and then find the transfer function I of S over V of S. Now, of course, let me present the correct result here. So in case you want to try out yourself sometime later, you can do so by comparing your result with the solution here. Right. This is the solution here. Okay. Denominator is what? Is the second order polynomial of S. Okay. So this is the pretty much the solution. I know the algebra step in the middle it's a little bit tricky. The reason is we are talking about symbols. Okay? We are talking about symbols rather than specified numbers. So in future, if they are specified as certain numbers, it should be much easier. Okay. Any questions regarding these things? We actually have a little bit left for a DC motor drive system. which kind of a mechanical system trying to go through the same thing. But I will leave that part to the next lecture a little bit, because we are not going through a mechanical system example here. So, right. Any questions? All right, if no questions, just the last thing, by checking out our Canvas module 2, exam time survey, I received most of you guys, most of the response. However, still about 11 students didn't give me the response. However, that will be counted as
because it's so like locked in our modules. I cannot open it.
It is showing locked in your module?
Yes.
That's weird. How many of you are going having that trouble, actually? Can you try to do it now even? Still locking? Or?
It locked right before class. I forgot to do it, so.
It locked right before the class. Well, that's not the mistake from instructor and the system, because that's the due date. That's the due time. You pass the due time, of course, it's locked. The locked we are talking about now is not that kind of locked.
No, I checked the last night too and day before, but it showed me locked that time. And I supposed to like it will be open in maybe on 14. So that's why I did not let you know about that.
And also here, Wally is reminding you guys that you have to complete the previous module to unlock this module. Did you do that? What I'm saying is here is look at here. Okay, let's take a look this module 1 and module 2 as example. Look at module 1. You see this document, beneath it there's a view, right? Beneath the syllabus you have view again. Beneath this you have another view. Beneath this you have nothing, and no assignments either. View, and view means what? You must finish these 3 views to be considered as finish this module. You finish this module, and then you can open the next module 2. You can look at here. Prerequisites of module 2 is module 1. And how to be considered as finishing the module 1? You need to do this, view this, and view this as minimum requirement. Take another example here. Module 2, what do you have? View this guy, right? And view this guy, right? And nothing to homework 1. Nothing to exam time survey because I remove it. I remove the submit. However, look at the text run exam. You must submit or say conduct these test run as well as the uploading the answer to be considered as finishing module 2. Upon finishing module 2, you're able to unlock module 3 because the module 3 prerequisite is module 2. Actually, I'm not 100% sure if this is the issue you have, but does everyone notice this? Is this something everybody aware? Prerequisite and the requirement of the modules?
Don't require check marks, correct? Just your screen is showing check marks?
My screen showing check marks. Where is the check marks?
Because like on mine, it'll show a circle on the ones that are required to view.
Oh,
and then like
different view. Okay.
On like homework and.
Let me see. Hold on. My check marks, it doesn't mean the requirement. My check marks, it just it means the
yeah. So the ones with the bubbles.
My check marks, it doesn't mean that. My check mark doesn't mean that. That means it's published or not.
Okay.
Thank you, Molly. And for the feedback, how about the rest of you guys? You have to follow this requirement. Otherwise, you are not able to unlock the next. Yes, you see, I didn't do anything here. That's why it's locked. You see this locker? Okay. If you have fully aware of all of these, that's very good. If you haven't, please immediately catch up. Because more importantly, you have a test run exam to conduct. If you miss that one, well, you miss the opportunity to become familiar with the lockdown browser. Well, who knows if that's going to be a problem in the exam, right? Did I make myself clear? This is regarding how to use the canvas, okay? If at the beginning of the semester, I provided some kind of tutorial material for the canvas use. So if you need, please review those. Okay. Any further questions? All right, thank you for attending today's lecture, and talk to you guys on Wednesday. Well, of course, the lecture happens right after the due time of the test run exam, and maybe in the lecture we will talk about it a little bit. And actually, I received the very important and helpful feedback from Molly already, and really appreciate it. And the rest of you guys, please remember to conduct it, okay, and provide me the feedback. Let's see how it works. Okay. All right. Thank you. And talk to you guys on Wednesday. Sure, no problem. Thank you, guys.